Good morning, everyone. Welcome to the first early career session of this conference. I apologize for the delay due to technical issues. We'll still aim to finish at 12:30. It's my pleasure to introduce the first speaker of this session, Dr. Bo An, standing right here. So Bo got his PhD in 2011 from University of Massachusetts Amherst under Professor Victor Lesser, and his thesis received the IFAMAS Distinguished Dissertation Award. He then worked as a postdoc with Professor Milen Tambe, and then we overlapped briefly when he's faculty now at Nanyang Technological University, so he used to be my colleague at some point in time. So this gives me a special pleasure to introduce him. So welcome to Bo, who will be talking about his work on security and sustainability.
Thank you, Edith. It's my honor to be here to report our work on game theoretical analysis on security and sustainability. So, game theory for security is a new and very hot topic over the last few years, and it's been pioneered by Team Core Group and USA, led by Professor Milen Tambe. And in addition to publishing top venues like IJCAI, the amazing thing about this line of research is we got lots of deployed systems applied in many places, including U.S. Coast Guard to help Coast Guard to patrol in the waterway, and to help Federal Air Marshal to schedule air marshals on flights, and also to patrol on the trains, to help police to patrol on the trains, to catch up ticketless travelers, and also to protect wildlife in Asia and Africa. So this theory behind this line of research is something called security games. So basically here, it's a game between two parties, the government agency, which is called Defender, and the terrorist or the adversary. So here we want to protect different targets of different importance, and the adversary might be strategic. They might conduct surveillance and then decide their best response. And the game is called standard game, where the security agency will move first, and then the adversary will move next. So the game can be normally represented such kind of matrix where there are some defender actions and attacker actions. And the solution concept here is called something called Steinberg equilibrium. And our contributions so far are including designing algorithms for solving very large scale games. For lots of games like this, the strategy space of both players might be huge or even infinite, or the number of actions. And another thing is how to learn adversary behavior, especially in the last few years, people have started to work on domains with lots of data. And also, as I mentioned, there has been lots of successful applications. And fortunately, I was working on some applications because I started to work on this when I was a postdoc at USC. So over the last few years, we have been looking at some very interesting problems, research problems, in how to analyze very complex security games. There are some examples here, for instance, security games with dynamic payoff, where the payoff of some target might change over time. And also lots of security interactions on networks, including transportation networks, terrorist group networks, those types of things, and also looking at some other aspects like protection, externality, uncertainty, and also strategic deception. And we also did some other work which are more motivated by applications such as cybersecurity, adversary machine learning, and how to protect coral reef, how to stop nuclear smuggling, and also how to protect elections, those types of things. So how to solve those, we combine techniques from AI, operations research, and game theory together to come up with a solution to this. When we are working on those problems, we always want to hope that those techniques could be applied in the end. So we want to really marry theory with practice. And during this process, the techniques we developed could be applied to other domains as well, with some proper tuning and extension. Given the time limitation, so I'm going to quickly go through some problems we have been working on over the last few years. And I might just tell you what's the problem and high-level ideas and some interesting results. So this is so the first problem is about security games with dynamic payoffs. So I use Boston Marathon as a motivating example. So in 2013, there was a bombing in Boston Marathon, and 3 people died. And later, we look at the Boston Marathon line. It's kind of straight line with about 40 kilometers. And if we think about if you are a police officer, and definitely we need to allocate security resources to protect this, such kind of events. So the Boston Marathon, it's a long line, 40 kilometers, and it will start from 8 a.m. to 12 p.m. And so the terrorist people want to attack more, want to kill more people. So one idea to allocate security resources is you can uniformly allocate security resources along this line. And we can divide the whole line into many small segments, and we can treat each segment as a target. And one interesting thing about this is you might see the number of people and different targets might change over time. And AM, we might see more people here, but 12 p.m., we will see more people here. If all the resources are evenly distributed, so the probability of catching the anniversary is always the same and different location and over the time. So at 12 p.m., it's easy to see that the anniversary will attack this point because that's where the game is finishing, so we will have more people on the finish line. And that's exactly what the anniversary did. But you might think, what's the point of still putting some resource in this place? This is where the game gets started, at 12 p.m. Because that time there are not many people here, so it's kind of wasting of security resource to still have security resource at this point. So the simple idea is perhaps we can do something smarter. We can kind of dynamically allocate security resources through this whole event. So that's the idea. Here we can see that we have different targets, and target value may change over time. So the target value, how this change could be some function, for instance, piecewise linear or whatever. And the idea here is we can dynamically allocate security resources. And keep in mind that when we are transferring resource, the resource is not protecting any target. So the key question here is how to compute the optimal strategy. I mean, how to optimally allocate the reallocated resources. Because here, time is continuous for both players. Because for the defenders, they have to choose when to switch resource, reallocate, and for the adversaries, they will decide when to attack and which target to attack. So we start with some, this is what we want in the end. So we start with some simple model where we think the transfer time can be ignored. So we can just quickly transfer resources. So if we want to compute the optimal strategy and a single time point, that's easy. So we can just compute minimax strategy and any time point. But here the problem is we have, the time is continuous. We cannot apply that. So what we found is even the optimal strategy will not change continuously. So the optimal strategy at 8 a.m. might still be optimal for the next 5 minutes. So that's something we can exploit. So there are some examples, but I will ignore the details. So the whole point of this idea is we're trying to find out the time point where we have to switch the allocation. So we find out those time point and compute the optimal allocation, those new point, and do that reallocation. Because here, transfer takes 0 time. So if we want to consider more complicated situation where transfer takes time because when the resource is in transfer, the security resource is not protecting any target, it's much more complicated, and technique I just mentioned will not work. So how to solve this? So what we did is, for this continuous time game, we construct a new game where the transfer time is a discrete set. And we can easily solve the game with discrete set strategy, and we can prove that the equilibrium of the discrete set strategy is still optimal, it's still the equilibrium of the original game. And for this problem, because Boston Marathon happens once per year, we feel it's more reasonable to compute the optimal deterministic strategy for the defender. And later we consider other scenarios where, like for a city, there might be bar street and museum. In Bar Street, there will be more people in the evening, but not many people during daytime. But museums, there will be more people in the daytime and not many people during the evening. So we might put more people in the museum during the daytime and more people in the bus street. So this is still some kind of, there are many targets, areas to protect, and those areas are of different importance, will change over time. But here, because this happens every day, it makes sense to compute the optimal mix strategy. And this is far more difficult than as compared with computing optimal pure strategy. So how to solve this? The idea we use here is, instead of computing optimal mix strategy, here we compute something called compact strategy. And this is something like called coverage, basically says the probability of protecting some target and some time. And we can solve some kind of equation to compute that. And instead of, for this coverage, instead of computing the optimal mix strategy, because that might have infinite and continuous support set, we design some sampling techniques. Because every day we just need to sample one pure strategy for the end users to use. And still here we just consider zero transfer time. If we consider non-zero transfer time, we can do some approximation. We can discretize the time and also and solve that. And we can prove some bound, and also for the discrete time case, we're able to apply some techniques to compute the optimal solution in polynomial time. We also look at some security game problem on networks. So here's one example is about how to detecting potential terrorist or plots. So this is motivated what's happening in Paris in 2015. So those two brothers, they launched a tank in Paris, and about 3 hours later, the third guy, they launched another tank and another supermarket. They killed, in total, they killed more than 10 people. And this is fully coordinated attack. And the French police recognize those two guys, feel those two guys are kind of suspicious. So those two guys were monitored by French police for about 2 years, and nothing happened. And they know that they were monitored. And later, French police felt they didn't do anything, so they stopped monitoring, and they found it time to attack. So, so here the problem is, for every country, they might know that some people are suspicious. Even for small countries like Singapore, they know that some people, went to Afghanistan and they might got some training there, but so far they haven't done anything yet, so the government cannot arrest them. So they will put resources to monitor them. So every country has this kind of special team on this type of mission, and there has been lots of release documents about this, especially for UK. To monitor one person, we need 5 people. You have to follow them, you have to listen to their phone call, or you have to keep eyes on how they're doing on the web. So all those types of stuff. So we have to limit resource. So we're looking at this problem. So we think there's a network formed by potential terrorists. And what the terrorist planner wants to do is they want to resolve a subgraph, connected subgraph of the original graph. Why it's connected? Because they hope that they can coordinate. That's exactly what's happening here. They call each other about 15 days before they launch their attack. And what the defender can do is they'll pick some nodes to monitor. And if there's overlap, the defender will win. Otherwise, the defender will lose. So that's a game. Here, the difficulty in solving this problem is the strategy of both players will exponentially increase with the size of the graph. So we come up approaches to solve this. So the idea here is something called a double oracle. So the idea is that we start with some small game which is subset of strategy of the original game, and we solve that, and then we compute both players' best response, and if the response are not in this original game, then we end that until this converge. But even the best response problem are NP hard, so we design lots of approximation techniques to speed that up until we can solve, scale up to real-world size problem. Another problem we look at is something called coalitional security game. So this is a graph about terrorist groups in the world from CIA. So CIA says this interconnected nature of those terrorist groups brings a big threat, and it's super important to break the linkage. But we don't have that power to break all the links. If we can only break a small number of links, which link should we break? So we model this as a coalition security game where we have an original terrorist network, and what defender can do is we can break some edges. Then on those remaining graphs, which may not be fully connected, those potential terrorist groups, they will play some coalition game because they are not fully cooperative. They will cooperate if they can receive higher revenue than not cooperating. So cooperative games are difficult to solve, but here we have another level which is more difficult to solve. So I guess we come up with approaches to solve this, including this branch and bound framework to solve integer program, and for on each load, each leaf load, there's a linear program, still not just scale. We come up with a solution to solve that linear program. I will not touch the details, but still combine techniques from AI operations research and some other areas. Another thing we look at is something called protection externality. For instance, when you are protecting one target, that resource might be protecting other targets as well. For instance, when a police team is here, the police is protecting all the targets within this purple circle. And when there is a protection externality, the problem becomes harder for security games without uncertainty. For protecting some targets, this is basically polynomial time solvable. But if you have protection externality, this becomes MP hard. To solve this, we develop techniques by combining different techniques to solve this. And for this problem, we still assume that we can only put the resource on targets. So if we want to, on those targets. But think about this problem. If we have two targets, one is here, and if you put a resource on this blue targets, it can cover all the put a resource on this blue targets, it can cover all the targets within this blue circle. So if you need always put resource on targets to protect those targets, we need two resources. But we can slightly do better if we relax that assumption, if we can put a resource everywhere. So the problem here is how can we optimally allocate security resources on those 2D continuous plane if we can put the resource anywhere. And this problem is even harder. And we developed some techniques to solve this. I will ignore the details based on grid shifting. So we build some grid, and for each grid we build some strategy. And the allocation should not overlap with the grid lines. And we shift the grid. We have many grids, and with that, we only consider the restricted strategy set. If we compute optimal strategy, we can still get some quality guarantee. And with those kind of strategy set, we're able to apply ellipsoid method very efficiently. And this can be applied to some, even this is only for zero-sum game, but it can be applied to some quasi-zero-sum game, which widely exists in the real world. We also did some work how to interdict network flow. So there are like drug flows from Mexico to US. So here it's more challenging because now the defender strategy is a flow. It's not just a path. And there's no compact representation for their tanker strategy. And because of that, all the existing works like Taobao will not work. So we developed techniques to solve this. It's somehow similar to Taobao, but it's fundamentally different. And for those, like for this problem, we still assume we know a lot. We need to make an assumption about the adversary's behavior, and we know not to pay off one of those type of things. So we just did something on kind of more repeated network interdiction problem, where we make zero assumption about the adversary's behavior. And we do not need to make assumption about how the behavior model of adversary, and also we do not need any knowledge about the adversary. And we assume this will happen forever. So the objective here is like every day the police set up some checkpoints and observe some interdictive flow, and based on that to decide what to do next. This is more online setting, and our objective is kind to minimize the regret. So the difficulty here, one thing is we have really partial observation because we can only observe the interdictive flow. We don't know what's happening with the flows where we didn't put any security resource. So we come up some exploration approach to come up some unbiased estimator to estimate the flow, and also to exploit based on the estimate flow. And in the end, we can get sublinear grid bound. So this is the problem. Another interesting question is, in most of security games, we assume that where we want our tanker knows all this strategy of the defender through surveillance. But sometimes their tanker might have some secret information. The defender might have some private information, for instance, the number of resources. Another thing is, in real time, we see lots of plainclothes protection. So we want to analyze if the defender has some resources, has some information to hide, whether hiding such kind of resource is a better option as compared with fully disclosed all the information. So this is called strategic deception, and we analyze this by such kind of sequential game where the defender strategy, in addition to this real coverage, the defender can send out some signal, which is singular strategy, and their tanker can observe the singular strategy and update the belief. And so I'm going to just mention the final results. There's something very interesting, which is for games which are zero-sum, PB is better, so it's better to hide some information. This is kind of intuitive because if it's zero-sum, SSE is equivalent to Nash equilibrium, but PBE, because their tanker has some uncertainty about the type of the defender, they might make the wrong choice. But for games which is kind of far from zero-sum, SSE is better. So for real-world problems, terrorist attack is closer to zero-sum, and for some domains like illegal fishing or patrol on the trains, it's more non-zero-sum game. So we also do something on cybersecurity, how to stop spear phishing, and to set up the personalized threshold value for those machine learning classifier. Because of time, I will not talk about detail, but basically here our tanker wants to steal some key information from different users, and their tanker might use some sequential policy. And so our tanker's problem is solving MDP, and what the defender can do is trying to control the transition probability of that MDP. And also, we just did some work on how to optimal tank a machine learning classifier. If under two conditions, when one is we know the classifier, and another thing is if we do not know which model the system is using, how to deal with that. And just we will start to work on some smart traffic control system security, where, for instance, there might be some bad guys who rob at a bank. They want to escape from city. They might control some traffic lights so that they have one way to escape. But the defender, and also when they control the traffic lights, they can also stop all the police people because they will get stopped on the roads. So we want to learn what's the equilibrium strategy for both players, for the defender, how to allocate the security resources to catch the bank robbers, and also how to improve the robustness of those classifiers used by those apps who will decide whether this highway is congested or not. I just use the last 1 minute to mention we also did some work on applying those ideas to compute optimum policy for the government. So there are two examples. One is how to set up the optimal taxi price for cities, because after the government set the price, the taxi drivers will play some game. And another thing is where to set up EV charging station, because after the government sets EV charging station, the drivers will play some kind of congestion game. So let me conclude. So there has been lots of amazing high-impact research going on those security game stuff and lots of deployed systems. There has been lots of new development on and learning anniversary behavior in data-rich domain and also cybersecurity, and there are lots of future challenge. And for computational sustainability, I guess there are lots of problems with lots of in which human beings are involved. And so those ideas could be applied, and also how to combine those game theoretical thinking with machine learning to make the learning algorithm more robust. So in the end, I want to thank my mentor, Milan Tambi, for introducing me to the field and the guidance over the years, and also many collaborators. Thank you.
So there's a microphone over there, I believe. So if someone wants to ask a few questions to Bo, there's an opportunity to do so now. So questions from the audience? So raise your hand so I can see you. So I'm afraid that this is too intimidating a room for the audience questions. Still, anyone, maybe someone who is sitting close? Okay, over there.
Hi. Yeah, I guess it is at least theoretically possible to, disrupt the traffic signals and, block the police traffic and somehow escape the scene. But I wonder if there's a more conventional case of controlling the signals to optimize traffic flow, perhaps under certain sport event where traffic is a big problem. And people trying to, maybe play a game. And I don't know how common or people are really thinking about, rerouting themselves to a better route, or, just blindly follow Google or Apple for their navigation. I wonder if you have any thoughts on that.
We haven't done anything yet, but I think that's definitely something interesting that's more complex. Okay, thank you.
Let's thank Bo again. Okay. Our second speaker of this session is Piotr Faliszewski. Piotr obtained his PhD in 2008 from University of Rochester under Lane Himmelsponder, and then he returned to his native Krakow, and he's been a faculty member at IJCAI University of Technology since then. So Piotr works in the area of computational social choice, and even though he's still a fairly junior researcher, as evidenced by him speaking in this session, you can say that he's been among the early founders of the area, people who've been working in the area from its very inception. Right, and right now he's doing very exciting work in this area that I believe is at the forefront and is among the most exciting topics in that subfield. So Piotr will be talking to us about community scoring rules, a special kind of multi-winner rules. So welcome to Piotr.
Thank you very much. So this talk is about community scoring rules, a call to arms. So the point of this talk is somehow to encourage you to study this topic as well. But I guess I'm not sure how to use this thing, but it works. So the topic is about committee elections, so choosing groups. But to put it in context, let's start from what so-called single winner elections. So if we want to choose one winner, a president, a meeting time, what do? We start with a bunch of candidates. We agree on we have some preferences. The voters know which candidate they like best. We apply some voting rule, and eventually there's a winner. And my claim is that essentially all voting rules are the same. All they care about is electing someone who is ranked as highly as possible by as many people as possible. And the only difference between single winner elections is if they care more about someone ranked as highly as possible. If you're electing a president, it's perfectly fine that a large minority of people is dissatisfied. 51% of the population can elect a president. So as highly as possible is important for presidential elections. If you're choosing a meeting time, then maybe as many people as possible is more important. So if 90% of the team can attend a meeting but they're not too happy with it, that's still fine. And that's completely different than in the world of multi-winner elections. Here we have fundamentally different applications, and we have to find good rules for each of them. We may need to choose a parliament. And if we're choosing a parliament, we care about proportional representation. We want the society to be represented well. Or we may need to decide what movies to put on a plane. Almost all of us came here by planes, often quite long travel distance. And there are movies available. Someone has to choose which ones to put in. And the criteria for putting movies on planes are different than for electing people in parliaments. Maybe you want to have just a few blockbuster movies, even though maybe 70–80% of the passengers prefer to watch blockbuster movies. But then for the 20% of the remaining ones, we can use all the other entries we have in the entertainment system. When choosing parliaments, we care about proportionality. When choosing items to be used by a group of people, we care about diversity. If we're making a shortlist, if we want to invite people for interviews to eventually hire someone at a university, we need to create shortlists from these hundreds of applications that appear, and this is a multi-winner election as well. And what we care about is mostly excellence of the candidates. So if there are great candidates, we want to invite them, even if they're quite similar. And these applications are fundamentally different. So in the single winner case, I claim that every single winner rule works okay for single winner applications. In the multi-winner setting, you need a different rule for different, fundamentally different applications. And trying to understand which rules you need is more or less what I study. So starting from single winner scoring rules, the setting is as follows. We have a set of candidates, in this case red, orange, pink, blue, and green, a bunch of voters. We're assuming that they represent preferences as rankings. So for example, here the first voter thinks red is best, then orange, then pink, then blue, then green, and so the other voters. And we will be looking at scoring protocols, scoring functions, and they work in a very simple way. They simply associate scores with positions. So here we have so-called Borda scoring functions. It's a simple linear function. So all it says is if you rank the top position, in this case we have 5 candidates, top position means being better than 4, you get 4 points. If you rank at second position, you're better than 3 people, you have 3 points, and so on and so on. It's also sometimes used approval scores. And in fact, in this talk, we will mostly focus on approval scores. And they simply say that, say, under K approval function, top K people get 1 point, the other ones get 0. Here we have an example with K equal 2, so top 2 positions get 1 point each, other positions get 0. The way single winner scoring rules work is that we have scores associated with position, and each time a candidate is on a given position, this candidate gets this number of points, we sum up the points, whoever has most wins. That's extremely simple. And now we want to move to electing committees, to electing groups of people. And single winner scoring rules are actually simple. They're very easy to understand, they're very natural. In the world of committees, we're entering a whole new dimension. These things become actually possibly very complicated. And it starts with a notion of a position. So in the single winner setting, we're associating scores with single positions. Here, when we have a preference order and when we have a committee, like this one, we have, in this case, example of 3 people in the committee. The position of this committee is not one number. It is actually a vector of numbers of the positions of these guys. So the red guy is on position 1, the pink lady is on position 3, the blue guy is on position 4. So the position of this committee is a vector 1, 3, 4. And now a simple analogy of single winner scoring rules is a committee scoring rule, so a function that associates a score with every position. So with a vector, in this case of, say, k numbers, if we have k committee members. And you should already see that we have an amazing combinatorial explosion of possibilities. Because in the single winner setting, we had m candidates. There are m scores, easy, polynomial amount. But in the committee setting, we have m candidates. We have committee size k, which can be taken as a variable. So there are m choose k possibilities for scores. So we have an exponential explosion. And throughout this talk, I will actually focus on explaining this class of rules. We'll do it through example, but first, two interesting, well, I was about to say an observation. It's a single slide in my talk, but as a paper, it's 50 pages of pain. It's an axiomatic characterization of the class of committee scoring rules. So there's a classic result of Young that characterizes single winner rules. We extended it to characterization of committee scoring rules. It still works. Essentially what it says, if you care about a few basic principles, committee scoring rules are your only choice. And in the case of multi-winner elections, it turns out that it's not such a small choice. We actually have a lot to choose from, and that's nice. And committee scoring rules have some other nice properties. One of them is whenever you rank someone higher, this person actually does better, so that's nice enough. However, instead of looking at these very specific axiomatic properties of committee scoring rules, let's just go through an example. So usually when we talk about elections, we think about electing parliaments, electing presidents, maybe sometimes electing some smaller things. This talk will be about business. So let's imagine we're running a store. Let's say shirt store, whatever, will actually move between different items. Let's say it's an internet store. We want to sell as many shirts as possible. We have M available to choose from, so we have our delivery companies that can give us M different shirts, like these ones. But we can only put K on display. So in case of an internet store, simply when you go to the homepage of the store, there are K shirts that can show up, maybe 10, maybe 6, maybe 15, but not too many. And for the sake of this example, let's assume that a customer thinks that the top K shirts in the universe of these M shirts are excellent, the top 3K shirts are very good, and top 10K shirts are good enough. So of course these are just arbitrary numbers. All I want to say is essentially I just want to create 3 categories here, but I will mostly care about excellent shirts anyway. And now the committee scoring function is a function that this is a function taken from the point of view of a customer who visits our website, and he sees these K shirts that we decided to put on the homepage, and the positions of the committee are just the ranks of shirts according to this particular voter. And this function, let's say, gives us the number of shirts this customer is willing to buy. Okay, so of course, depending on what type of customer we have, we'll have different functions. So for now, we just have this large area, large space of possible committee scoring rules, these functions that we can choose from. But how do we choose? Depends on the customers. So let's say our first customer comes in and says, I will only buy a shirt, only one shirt, if it's the very best among the shirts I like. So you can clearly see that this is not a nice person. And you don't want customers like that, maybe. But if these are the people you have to deal with, well, you can use a committee scoring function like this. And you can see that this is function that says alpha 1, it means approval 1 of I1. So approval 1 means if this if the best shirt in the store is among one best shirts according to his customer, we give 1 point. So he sells 1 shirt. So that's nice. Okay, that's exactly modeling what we have here. The other parts of the function are actually irrelevant because they will always be 0. But this function actually defines SNTV, single non-transferable vote, voting rule. So essentially the assumption that we have customers that are only willing to buy the very best thing that they think in the world exists, then in fact this is exactly a well-known voting rule, well-known committee rule. This rule is polynomial time computable. This rule belongs to the so-called class of separable rules, which means that it's possible to express its scoring function as a sum of single winner scoring functions. It's also a representation focus, but let's ignore that for a while. And it's a function that is committee monotone. It's a rule that's committee monotone, which means that as we increase, let's say if we increase the capacity of our store, say from 10 to 15, then we'll just add 5 new shirts. We will not replace the old ones. Okay, so in the world of committee scoring functions, we have now a new class of separable rules, which sum up scores. And we can, in fact, axiomatically characterize this group as exactly those that when you extend the committee size, you only add new things. You cannot remove anything and replace, you can only add. Okay, so we have a new customer. And this customer says, I will buy, here we have a new customer. And this customer says, I will buy all the excellent shirts there are. So among all these K shirts, the green lady will look around and says, I buy all of them as long as they're excellent. So we can describe her buying function as a sum of K approval functions. So she looks at every item, she looks if it's excellent, if it's among top K, if it is, she adds it to the list, she buys it. And of course, you can say, nobody behaves like that. When I come to store, I buy maybe 1, 2 items. But actually, if you come to a store regularly, then over time, you will actually possibly buy all the excellent stuff there are. So if these are not, let's say, shirts, maybe not all the excellent shirts. But if it's a toy store, and you come with your kid, each time he will see a toy that he finds exciting, and eventually you'll keep buying the whole store. But it turns out this is the block rule, a block committee rule, which is also polynomial time computable. It's weakly separable, because it's a sum of separate functions, but all of them depend on the committee size. It's also a kind of, it's called top K counting, which is a technical term. It satisfies certain axiomatic properties, which I will not go into too much. But now, in fact, our world of committee scoring rules looks more interesting. We had separable rules, now we have weakly separable. And it turns out that all weakly separable rules, all those that are like block, can be axiomatically characterized by a certain monotonicity notion. We also have top K counting rules, which can be characterized by a simple certain principle of behavior. Within weakly separable rules, the separable rules are also fully characterized axiomatically. And now let's have a deeper look into the nature of these two very simple rules. So let's look at how SNTV and block and a K-border, which I will explain soon, behave. So under SNTV, let's imagine a simple experiment. Now we have a world of different shirts and different customers. So what you see here is a diagram generated from 4 Gaussian distributions located on extreme ends of the 2D axis. And there are darker points and there are lighter points. The darker points are shirts. The lighter points are actually customers. And this is the space of preferences. So a location on this 2D diagram means that if you're in a particular location, it means, for example, the more to the left, the more colorful shirts you like. The more to the top, the more formal shirts you like. So people are represented by what they like among shirts, and the shirts are represented by their properties. And if we're using SNTV, this function that describes behavior of a customer who will only buy his most preferred item, then committee of size 1 is just this red point somewhere in the random. And as we increase the committee size, you can see this looks quite random. We just keep on adding somehow strange points without much structure. And this is actually how SNTV behaves. And this means that if you have a really picky customer who will only buy the best thing, it doesn't actually model t-shirt store. There are no people who are so particular about their t-shirts, or very few of them at least. This is a function that describes a customer who's buying extremely luxurious goods. So he's willing to pay, or she is willing to pay a lot of money, but only for something that the person really appreciates. And this means that the fact that we see absolutely no structure in this committee means that there's no point pre-producing luxurious items. This somehow what this tells us is that if you're producing luxurious items, you have to make them on demand. And that's quite an interesting conclusion that you get from analysis of a very simple voting rule. Okay, so if we move to the block function, by the way, we also in the SNTV we also see that as we either increase or decrease, we only add new things. When we move to this block function, which means I will buy all the excellent things I find, maybe not once, but not on the first visit to a store, but eventually I coming to a store and I will buy it, then the rule behaves like this. So it identifies the centers of the Gaussians in a certain way. It's a bit chaotic because it identified two of them well, one of them okay, and one of them poorly, but it still did. And it's quite an interesting behavior. And we also saw that this function is not committee monotone because things were disappearing and moving around. And as a sidetrack, I will also mention that there's a rule called kborda, which instead of using these approval scores, just use the linear function. And this is, just as a side comment, this is exactly a function that describes shortlisting. So if we want, so here we have definitely committees, so the items that are chosen are similar to each other. Okay, but let's move to yet another experiment. So what you see here are 4 distributions of candidates and voters in this 2D space. What we did here, we generated exactly the elections as like you've seen before. So on the bottom you see the 4 Gaussian thing, and above are uniform square, uniform disk, and a single Gaussian. And we ran 10,000 elections of each type, and we aggregated histograms so that for SNTV, we get this. The bluer a particular point is, the more frequently in our experiment we chose a person from there, an item from there. And you can see that SNTV perfectly copies the distribution that it starts from. And this is more or less another way of seeing that if you're selling luxurious items, there's no point in pre-producing, there's nothing to focus on. You simply more or less have to just match your clients, and you have to do it on a one-by-one basis. And another argument for that is that we get exactly the same pictures if we choose committee of 1. Also, it's the fact that we're copying the distribution so well is essentially the fact that it's a random artifact because we keep on repeating elections. That's why it happens. So from the point of view of politics, this just means SNTV is a useless rule. But from the point of view of selling items in a store, this is actually quite good because we never have a single election that actually tells us what to run. Each time a customer comes to the store, he's probably the person, he or she, sees a distorted view of the products. So he will or she will rank them differently. Okay, kborda focuses on the best things. And we will not focus on that too much, but we will focus on block. So this was buying K-based items. So buying toys for children or buying our excellent shirts. And this, again, shows very strange behavior from the point of view of politics, but it shows very good behavior from the point of view of economics and selling items, because what it says, if our customers are simply willing to buy good items, and they will keep on returning to the store, and they will keep on buying items. These are relatively inexpensive things like toys or shirts or shoes or things like that. What our experiments show is that you cannot focus on mainstream, so not like kborda, you don't choose from the center. Ignore the center, these are the things that no one likes too much. But choose somehow not exactly extreme, but choose things that are somehow characteristic. And that's a nice lesson to learn, and it's interesting to show that committee scoring rules can actually identify this sort of behavior. Okay, we also had some experiments, which I will not describe, with non-matching distributions of voters and candidates. But let's have another customer. Now our lady says, I will buy only 1 shirt if it is excellent. So if there is at least 1 item in the store that the lady ranks as excellent, she will buy it. So this models 2 kinds of stores. Maybe it's a shirt store at an airport. You're not going to return. You will not buy K shirts arriving each time to the store. You know, maybe some people come to a given airport quite frequently, but most people don't do it so often. So it's either a shirt store at an airport, or more realistically maybe, this is a car dealer. So our shirts now become cars, and you only buy a car once every 5-10 years, and it has to match your preferences. You buy the excellent one that you can find on the market. And the function that describes it depends only on the top preference of the available items. And it's in fact the approval-based Chamberlain-Courant rule, again, something known from the literature. It is NP-hard, but it can be computed approximately. It has some interesting features. In particular, it satisfies certain axiomatic notions. But what we will focus on is actually how it behaves in our 2D experiment. So in our 2D experiment, what you can see again are the 4 Gaussians, and as we increase the size, I hope you can see it a bit, it's actually essentially a facility location problem. So we're getting, if you're a producer of cars, and this is what Chamberlain-Courant approval function models, it means you should have every type of a car. And even more interestingly, if we look at the histograms, it shows that you should have every type of a car, but there's preference for extreme, which means, and this also is what you see in reality. You see these super extra fancy sport cars that don't seem so necessary for anyone, but they still exist. And we see it on the histograms here that there is preference for extremes, even though you generally want to just have things as they are, but there is that preference. Okay, and as we're running out of time, you'll see that we have plenty of other committee scoring rules, and they show up a lot, and you have a lot of variety, but the conclusion is that we have a huge map of different types of committee scoring rules. We know computational properties of just a few of them, and in the actual paper, there are specific questions that you can work on, and I can only finish with telling you, come join the committee side.
Thanks to Piotr for an excellent talk. Given that we don't have much time, we can maybe fit in one very quick question. Anyone? Okay, so
Then we cannot?
Then we cannot. So let's thank Piotr again. Thanks. Our next speaker in this session is Pingzhong Tang. Pingzhong got his PhD from Hong Kong University of Science and Technology under Fang Zhenlin in 2010, and then he's been a postdoc in Thomas Sandholm's lab for a couple of years. And after that, he became a faculty at Tsinghua University. He works on a variety of topics in algorithmic game theory and mechanism design. And today, in particular, he's going to talk about his recent work on large-scale applied mechanism design. So welcome to Pingzhong.
Okay, so today I'm going to talk about a topic at the interface of AI. Oh, okay, I need to stand there. Okay, so today I'm going to talk about topics at the interface of AI and economics. So obviously the other three are the same. So if you don't understand mechanism design, it's fine. So you can understand it simply as allocate resources and pricing. So So in particular, I'm going to talk about large-scale mechanism design at nationwide scales. So I'm going to talk about 3 case studies within this topic, and I'm going to categorize these 3 topics into 2 categories. So the first, I'm going to talk about a water right market design at Gansu province, China. So I'm going to categorize this as the first category because it's a low-frequency mechanism design problem, and it uses cooperative game theory, and the goal is AI for social goods. So it's more from a government point of view. And the second and third about dynamic bioimpression allocation in e-commerce, as well as dynamic reserve pricing in ad auctions. So these are joint work with Taobao, which is the largest e-commerce website in the world, as well as Baidu, which is the largest search engine in China. And this is the second category because it's more a high-frequency mechanism design problem, which I will define later. And it uses non-cooperative game theory, and the goal is to maximize revenue for the company. So the first one, what right market design? So theoretically, the theoretical model of this problem can be seen as a generalization of the famous assignment game. So we were going to start with a background introduction of what is assignment game. So we are given a set of buyers and sellers. So each seller may have multiple items for sale. May have multiple items for sale. And each buyer may demand multiple items. And we are given a bipartite graph with weight on edges. You can understand it as a model that with values on vertices as well. So the weight on each edge denotes the profit from trading one unit item between the buyer and the seller in the ending points. And the profit is going to be split among the buyer and the seller. So our goal is to find a matching problem, matching between the sellers and buyers. So if you are a computer scientist, you may wonder, why is this interesting? Because you know it's just a maximum matching problem to maximize social welfare. But there is a very important economic constraint here required to design these matching markets, which is the so-called core. Okay? So assignment is in the core if no subset wants to deviate from your assignment. So in other words, I do not want to deviate from your designated matching to form a small coalition so that each of the agents in the small coalition can bet off. This is a central solution concept in market design, which is repeatedly justified in practice, proposed by Gale, and written in a paper by Shapley and Scarf, and also verified by experiments by Al Ross. So in particular, in the seminal work by Shapley and Shubik, who consider unit demand and supply model, which means that the buyer need at most one item and the seller can sell at most one item. In this setting, they prove a very beautiful results. So the results can be stated as an equation, which is the algorithmic solution is equal to the economic solution. So in other words, any maximum matching corresponds to a price vector in the market such that no subset of agents wants to deviate. Okay? So, for short, it essentially means that any maximum matching is in the core. Okay? So if you don't understand this, it's okay. So it's just say, it's okay to ignore economics. You can just find a maximum matching, and there is a price vector that will give you a very nice economic properties for free. Okay? And these results turn out to be very general, and it can be extended to multiple supply and demand setting. And in the seminal paper by Elderman, Olchovsky, and Schwartz, they use these results to show that the set of NV-free equilibria is essentially the set of stable matching in this multiple demand market. And they use this result to show that the revenue of GSP in any NV-free equilibria is at least the revenue of VCG. So this is a very general result. So now so we're going to apply this model to our problem. So before we apply this model, we want to introduce the problem domain a little bit. So what is water right market? So in the western of China, which is very dry area, a very arid area, pretty much the same as the western of Australia here. So there is the so-called primary market of water. So at the beginning of each year, the government will allocate certain amount of water to each village for agriculture. Okay, so as the time goes, certain villages need more water and certain villages need less water. That's why we need to design the so-called secondary market for the villages to trade waters among each other. And it turns out to be a very effective way to mitigate the water shortage and, of course, increase social welfare. So applying the assignment model, we can see this as a multi-unit supply demand assignment game. And the connectivity of the graph is defined by the geographic connectivity of the villages. But here we have a very important constraint called the threshold constraint. So this threshold constraint essentially means that any transaction amount between a buyer and the seller can either be zero, which means there is no transaction at all, or it must be above some threshold. Okay? So you cannot just trade 1 ton of water. It can be either 0 or above 50. Okay? So this is the so-called threshold constraint. This is actually a hard constraint defined by the local culture, as well as there are some administration costs as well as transportation costs if there is a transaction. Okay? And our goal is to maximize social welfare. So in our work last year, we considered finding the maximum matching in this graph algorithmically. So our finding is as follows. So the problem of computing the maximum social welfare flow is actually NP-hard, and even NP-hard to approximate. And we come up with dynamic programming algorithms on specific graphs, on graphs with structures, as well as integer linear programs on the general graphs. And then we can solve it at the current scale, which is about 200 villages. So even though the algorithm problem can be handled appropriately, there is one important problem remain, which is that the maximum matching doesn't automatically give you a price vector. So without price vector, you don't know the incentive of the villages. So how do you know that they want to participate in your matching? And the way we implemented last year is that we let the villagers to negotiate among themselves, which is hardly satisfactory because there are quite a lot of uncertainties in the negotiation. So this year in the Amas paper, we solved this problem in a Shapley-Shubik way. So our first result is actually negative. We show that the trivial extension of Shapley-Shubik results doesn't work because there are maximum matchings. Well, there is no price vector that makes it a core solution. So the core can be empty in our threshold model. But we do show that the Shapley-Schubeck results hold approximately. In particular, we define this solution called two-core. So a two-core means that no subset can benefit twice. So if the player says, you know what, if I cannot benefit twice, I do not want to deviate, then this solution is stable. Okay? So we show that there is a price vector that corresponds to the maximum matching in the threshold graph such that it is in the two-core. And we should also show a lower bound of 7/6. And we also give a full characterization of why the core is non-empty. We show that the core is non-empty if and only if the market graph is a disjoint union of trees and even cycles. And we did this on real market data and show that actually the tool is highly overestimated. So we actually found that no subset can benefit by 0.004 times. And the current progress is that we have implemented a simplified version of this algorithm in Gansu province, China. And we are currently at the early stage of an initiative to build a nationwide order-right market in China. And if you know this ancient canal built at 486 BC of China, which transport all the south water to the north, and this can be a restarting of that work. So the second part, I'm going to talk about a new type of mechanism design environment called high-frequency mechanism design. So a lot of the people here knows the standard environment of mechanism design, which is one-shot, perfectly assuming that players are perfectly rational, and we have a fixed set of players, and the type is usually one-dimensional, and we have an static, and there are many well-known examples. In particular, in mouse and auction, in single-item auctions, we know that mouse and auction maximize revenue in theory, and we know that generalized second price auction also is one-dimensional. Generalized second price auction also did very well in practice, in the practice of sponsor search. But in fact, a lot of important industrial environments has the following properties, which I coin high-frequency mechanism design problem. So it's repeated in high frequency, usually hundreds and thousands, even thousands times per second in execution of the mechanism. And the players are sort of rational. So they're rational for sure, but they're not like rational in the sense that they play Marsh equilibrium. Their rationality is reflected in the data, and the companies of these scenarios usually have a lot of data. And there's usually a dynamic set of players, meaning that today we have this set and tomorrow we have another set. The players come and go. And the type is usually very complicated. We have multi-dimensional valuations, we have budget, we have some deadlines for them to make decisions, and there are a lot of hidden market conditions that we do not observe. And we do not know what is optimal mechanism in this environment, in this high-frequency mechanism design environment. So the current status of industry is that, okay, since we don't have a mechanism for the high-frequency environment, why don't we just use the standard mechanism from this one-shot setting for this environment? So the problem is that these mechanisms on the new environment are usually not optimal. So for these companies such as Baidu and Alibaba, they hire a very large team, very smart people to tune these parameters. at least like 500 people in Baidu, I don't know how many in Alibaba. So they tune these parameters day to day to optimize their revenue and performance. And this optimization can be ad hoc, and it can be very costly. So the goal for the remainder of this talk is to design algorithmic procedures that automatically adjust and optimize mechanisms for this high-frequency environment, since the mechanism is executed many times per second. And the solution I propose in this talk is called reinforcement mechanism design. So let's start from this second case study called allocating bio impressions on e-commerce sites. In particular, I'm going to talk about how to allocate bio impressions on Taobao. So here is this problem. So we have like hundreds and thousands of impressions coming per second on Taobao. And these impressions come to the website. And then the sellers will set his price for the item and then input it onto the Taobao system. And after seeing the impressions, the prices by the sellers, Taobao will rank the sellers. Okay, you can understand this as a ranking problem, but as a game theory people, I want you to understand this from a resource allocation point of view. You can understand different rankings as different allocations of bio impressions. And different allocations can be implemented by a randomization of different rankings. So from now on, instead of focusing on the rankings, we just focus on how to allocate bio impressions, assuming that the Taobao has the power to do so. Okay? So give a ranking, and then the seller will observe his revenue today. And then he's going to design a new price and enter the system. And the procedure goes on and on. So the current industry practice is that they use recommendation algorithm to handle this kind of problem, this kind of ranking problem. Some websites use collaborative filtering, and a lot of other sites use the so-called contextual bandit, which use features of the buyer and sellers to predict CTR. All these solutions suffer from a very important game theoretical problem called susceptible to price manipulation. So it is widely observed on Taobao that the sellers intentionally post a very low price, even lower than their cost, to get more impressions today, which will help them rank higher and get more impressions tomorrow, because this algorithm takes price very seriously. So if your price is low, you have a high probability of getting ranked higher. And this will cause the price of the items fluctuate and the system unstable, and is widely regarded as one of the most severe problems faced by Taobao. So we have some standard game theory solution, but we then found that it is very difficult to apply. So then we proposed this new solution using MDP formulation. So quickly stated, we model each state of the decision maker, which is Taobao, the mechanism designer. The state is his current price vector of all the sellers and all the historical outcomes. So in short, you can understand it as the history. And then the action for each state is actually to give an impression allocation of this round. And the immediate reward is the revenue generated by the allocation of this round. And the state transition is defined by seller's model, which we will define immediately. The problem in the eye of a reinforcement learning researcher is that it has a high dimension with hundreds of sellers, and it has a continuous state space and action space. And the difficulty in the eye of it's also non-standard in the sense that the environment is kind of not static, it's dynamic in the sense that the sellers are part of the environment. Okay? So they are strategic and they are not stationary. So we use this so-called, inspired by this NIPS paper last year, we use this sellers model. So the seller's decision can be considered as a linear combination of statistics and rationality. So with probability 1 minus epsilon, so this is the parameter of the seller, he will draw a random price from his empirical price. And with probability epsilon, he will draw a price that gives him the maximum profits in the past. So if this goes to 1, this is entirely statistics. And if this goes to 1, this is game theory. And alternatively, we are currently implementing this model, which is to learn a general seller's model, which is that the observation of his KPI yesterday, key performance indicator yesterday, as well as some local features to the price he will set tomorrow. So with this model of sellers and with this MDP formulation, we are going to try different algorithms to implement this MDP, to solve this MDP. And we try some greedy algorithms, UCB algorithms, and we also tried deep Q network, DPG, and as well DPG. So it turns out, so when we end up with a modification of the DPG algorithm that makes use of the separability of the BIOS, and this algorithm is implemented by an actor network that gives a local allocation of each seller, and also a critic network that updates the Q value for each action by Taobao. So this algorithm iterates between the two networks until it converges. So GRU is a recurrent neural network implementation. So since I'm running out of time, I'm going to quickly go through the experiments. So we will implement all these algorithms, and we can see that DDPG do not converge, but our algorithm converge, and it gives the highest average reward. And it is also the case when we set the seller's cost to be a random variable. So I'm going to very quickly mention the last case study, which is to how to dynamically adjust the reserve price in Baidu. And this is currently implemented in a few median cities in China by Baidu side. So this is the typical sponsor search page. I'm going to skip it. So the problem is pretty much similar to the Taobao problem. So we have very high frequency execution of the Baidu mechanism. And there are a lot of user impressions coming each second. And the bidders place a bid today. And the mechanism observes the bid and returns some outcomes to the advertisers. So you can denote this by KPIs. And then the bidders will adjust their bids, and the mechanism goes on and on. Okay? So we are going to also assume a Markov property of the bidders. So we assume that the bidder's decision only depends on his bid at time t. So his decision at time t plus 1 only depends on his decision at time t, and his KPI he observes yesterday. Okay? So this is also a dynamic mechanism design problem, while the mechanism designer is the MDP decision maker. And the joint bits distribution can be regarded as states, reserve price for each advertiser. So the price vector as Baidu's actions as the decision maker's actions, and the stage transitions is defined by the beta model here. And the goal is to maximize long-term discounted revenue, which is usually 3 months or 6 months. And also the MDP is difficult to solve, as you can imagine, and we use some heuristics to implement to solve the MDP. So in particular, I want to quickly mention that the beta model we use here is a large recurrent neural network, and we tested on 6 gigabytes of data of 400 keywords over 9 months of Baidu bidding. And we can see the cross entropy is pretty small. So these are some data sets we select. This is the real one. This is the one that we learn. And we compare a bunch of benchmarks. So this is the current Baidu mechanism, and this is the static 50 cents, which Baidu used for 2 years. And we also have this static optimal, which essentially means that we use the buyer's previous price that works well for us as his reserve. And this greedy algorithm, which we initially want to use this as a baseline, but it turns out to work very well. Greedy algorithm essentially means that we randomly choose a bidder. We greedily change his reserve by either lower this reserve 5%, increase this reserve 5% will stay the same. We just consider these 3 actions. And the performance turns out to be very good. And the last one is our algorithm. And by comparing all these algorithms, you can see that our algorithm works the best, but the greedy algorithm works very well too. And the current Baidu curve is here. So it can be seen that by simulation, it has a 50% increase. So this is by simulation. So the assumption we make here is that the bidders will behave similarly as they did in the past 9 months. So we are currently have this, you can see it as a field experiments in Xi'an city and in Nanchang city. And the performance is not as optimistic as this one, but it's still very large. So the takeaway of this talk is that I introduced 3 cases of applied mechanism design at nationwide scale of China. So the first one is more from a government point of view, which is to increase social welfare of a water right market while guarantee incentives for the villages to trade. The second and third is talking about how to allocate resources, how to allocate impressions for large websites, one on e-commerce and the other on ad auctions. And for the second and third, I propose a solution framework called reinforcement mechanism design. So you start with the classic mechanism that is very well accepted in your domain, and you use reinforcement learning to optimize your parameters of the mechanism. But it's very important to notice that you must build a very well player behavior model. That's why you need economics and game theory. And also you need to make heavy use of data to define rationality in your domain. And of course, to solve these large-scale problems, you need recent progress of reinforcement learning. Thank you.
I'm afraid that in the interest of time, we'll have to take questions for Pingzhong offline. So our last speaker for this session coming up is Aviv Zohar. So Aviv got his PhD from Hebrew University under Jeff Rosenshine in 2008. Aviv also started out working in algorithmic game theory and social choice. So he then spent 2 years as a postdoc at Microsoft Research. He's now a faculty at Hebrew University. And recently he's been working in the very exciting area of cryptocurrencies. And this is what he's going to tell us about. So welcome to Aviv.
Okay, thank you. supposed to be a remote. All right. So this is, I'm going to mention a lot of joint work with many colleagues and students to whom I'm very grateful. So maybe I'll tell you how the story started for me to begin with. So one day in June of 2011, when I was doing my postdoc at Microsoft, I received an email from a friend. This friend is a PhD student at Berkeley for economics, and he just occasionally sends me interesting links to stories. So I followed this link to a newspaper article, basically, in an Israeli newspaper that talks about this new type of digital money that's supposedly very revolutionary. Right? If you follow every story in an Israeli newspaper, there's usually some blog post in a tech blog behind it. So here's the origin of the story. There was a blog post on a blog called Launch that basically describes Bitcoin as the most dangerous open source project ever created. So that's a very tall order to be the most dangerous open source project ever created, right? You'd probably imagine something more like this, maybe open source 3D printed killer robots. But I was really intrigued. What is it that people are doing that could be so exciting? And it took us a while to understand the protocol. I was very skeptical at first. I thought it was too good to be true. So what I'm going to tell you now is maybe more about how I process and understand the protocol after quite a while of working on it. So here's basically what cryptocurrencies and Bitcoin are trying to do. If you start with digital money, then transferring digital money is basically all about changing records on some computer. For example, if you look at the example here, maybe there are two agents, the blue and the red. They have account balances on some central machine, and they can issue messages, maybe saying, please move money from my account to the other guy, and these balances would just change in the machine's memory. What cryptocurrencies are trying to do, and this is the revolutionary part, they're trying to disintermediate this interaction, basically move the bank out of the equation and have everything done on a peer-to-peer network. So they basically aim to replace this central server with many, many machines that are spread out around the world. Each one has a copy of this same data structure, and each one basically holding the account balances and authorizing transfers of funds. So this seems like a very interesting idea. And the challenge here, the reason that Bitcoin is an innovation in technology, is that it solved a very important open question that was open up until then, at least. And that is what to do when you need to synchronize this data. So basically, it solved a problem that in computer science we would call the Byzantine consensus problem, which was previously solved in other environments, but it wasn't solved in an open internet environment, internet-like environment, where everybody can enter the system. So basically, each one of these nodes is an unknown participant. We know how to solve the Byzantine consensus problem in a closed setting. So what could happen here in terms of Bitcoin is that money, right, when we issue the order to transfer money, we can now do it in a way that tries to confuse the system. So for example, this blue agent can say, please move all my money to the red agent, or please give all my money to the green agent. And the system has to decide between these two messages which one it should accept. It cannot accept both. Okay, so these two messages can go to different nodes in the network. If they just apply them, we have inconsistency in the records, and we have basically nothing to do. And the complication is, of course, that this guy that's doing these confusion, that's trying to evoke this confusion in the network, is actually also in control of some of the machines that are there. Okay, so that's basically what happens. So now, Bitcoin solves this problem using a data structure called the blockchain, which is kind of a buzzword at the moment. It's the technology underlying Bitcoin, and it's being adopted by a lot of the major financial actors. So the blockchain is a very simple data structure. It's basically the collection of transactions that were approved by the system. So every block contains essentially just a set of these requests to transfer money that were approved. And when we want to add new ones, we just append to the end of this data structure new sets of transactions, and we keep everything consistent. So every machine on the network does this. If it sees a transaction that tries to use the same money again, it doesn't include it in the block. The problem, of course, is that this is a decentralized system, and we don't have any centralized control over who is creating the block. So it's very possible that two blocks will be created at the same time. Basically, two nodes in this network try to extend the history of events, of transactions, and they do it differently, right? The second branch here might be a block that extends the same chain and adds a transaction that wasn't, that is in conflict with the first one. So we basically have to choose between these two possible extensions to the chain. So the way to think about it is as if we have two alternate histories, right? If we read the blockchain from start to finish, we basically have a log of all the transfers of money, and if we agree about the blockchain, then we agree about where money is. So the way that Bitcoin solves this problem is using three main rules. The first rule is that all nodes adopt the longest chain and extend it. So the way I think about it, maybe because of my past with social choice and voting that Piotr talked about before, is in a way this is a voting mechanism, right? If you build and extend the longest chain, this is as if you're voting for that chain. You're making it longer, and then others that will see it later will think of it as even longer than before. Hence, there's in some sense a vote going on here. And this vote actually initiates a winner-takes-all dynamics. If you are voting for the longest chain by increasing its length, then future voters will also support the longest chain. The second rule maybe is to send your blocks very quickly. Once they're created, they get flooded to the entire Bitcoin network. And that's to have everybody have the same picture, the same view of all of the events. And the last one, and this is maybe the most important rule, is to make block creation hard. So block creation is computationally difficult on purpose, by design. And the reason here, there's an intuition that I might give you without going into the details, is that it makes it harder for attackers to add these votes as many times as they want. Right? If you try to add more blocks, you have to solve a lot of computational puzzles that are really hard to solve. And so you are left with a limited capacity, right? So unlike other voting scenarios where you might be able to just count the number of participants in the internet, it's very easy to forge identities, to have Sybil attacks. And so this mechanism is basically one that prevents you from voting many times. So of course, the thing that we have to defend in Bitcoin the most is the double spend attack. If somebody sees that he got money and it's somewhere inside the blockchain, the rules of the system are kind of scary in some sense. Somebody might show up at some point with a longer chain, and the rules that I just described basically say that the longest chain is the one that we considered as the right sequence of events that really occurred. So if somebody suddenly shows us a longer chain, we have to conclude that this payment that the blue guy got over there in the top chain no longer exists, and the money was actually, not his. It's disappeared, and it was rerouted to the green guy. This is called the double spend attack in Bitcoin. So Satoshi Nakamoto, the guy who invented Bitcoin, or the pseudonymous, his identity at least is known as Satoshi Nakamoto, basically gave us a theoretical result. It wasn't framed as a theorem, but it was later turned into one. And it basically says that as long as the attacker controls less computational power than the rest of the system, And as long as nodes can communicate quickly, then we can be safe. How can we be safe? In the sense that if we wait long enough for our transaction to be deep inside the blockchain, so for blocks to be built on top of it, then the probability of losing that money, of having that block replaced by a longer chain for some reason, decreases exponentially. Okay, and this is a very good guarantee because after a while it becomes next to impossible to lose money. So the last thing that maybe ties Bitcoin together is its underlying incentives. We want a lot of machines in the network to work really, really hard and to perform computational work. So one way to get them to do it is to pay them for that, right? So Bitcoin actually collects small fees from every one of these transactions in the block, and it adds some money that is created, and it uses that to pay the creator of the block. So whoever solves these hard computational problems actually gets paid with the currency itself. And that forms a very nice mechanism that incentivizes people to do a lot of this work, which is called mining. So at the current state of affairs is that mining is done on huge server farms. This is an example of one. It's a real business that basically prints money by running this code. And as a result, if you recall, everyone is safe. The network itself is safer because an attacker is less likely to hold more computational power than everybody else. So now I can finally get to our work on the Bitcoin protocol. So the thing that I would like to say maybe is that there are these two assumptions of Satoshi's theorem. And these are pretty much the center of every work that I've done, I think, on the protocol, right? Every attack on the protocol is somehow an attack on these assumptions. That's how you get around the theorem. You kind of destabilize its basis. So one thing is that we need to notice is that we don't really know what to do with the second assumption, that the attackers control less than 50% of the system. And we really have to replace it with some idea of the size of the system itself, right? If the system is really large, then attackers find it hard to be 50% of it. And so maybe the underlying assumption that supports that is that nodes have an incentive to participate that is really strong. So now, how can we attack these assumptions? One way to talk about the communication assumptions is to talk about the blocks, whether they can move around really quickly in the network. If they're slow, then that breaks this assumption, and this will tie into the scalability of Bitcoin. We can think of disconnecting the nodes from one another, and this ties into work about the network infrastructure. And of course, we can talk about the incentives themselves. They might not be as we thought they are, right? It might be beneficial to deviate from the protocol to gain more. So basically, I think all of the ideas presented by the previous speakers before me about security as a game theoretic notion, about voting, about mechanism design, they're all going to be present in this talk as well. So let's talk about the scalability problem. So Bitcoin actually creates blocks in expectation only once every 10 minutes. So this computational problem that you have to solve in order to create a block is really, really hard. A single block is created in the entire network approximately every 10 minutes. So that's in expectation. So that's a very slow rate of accepting transactions. Think of buying coffee and having to wait in expectation 10 minutes until your transaction is approved. And it also means that the rate of transactions itself is very slow. Every Bitcoin block is currently limited by 1 megabyte, although that's very soon about to change. And the transaction rates that this implies are very slow, only on the order of 3 transactions per second, which is just a very slow trickle. So maybe the first thing that we started to think about was how to change these parameters. What happens? Why was 10 minutes chosen? And why do we have to have such a low transaction rate? So it turns out that if you try to change these parameters, maybe increase the block size or have a higher block rate, you end up with something that looks less like a blockchain and more like a block tree. So if you look at this, for example, several blocks by nodes can be created at the same time or nearly at the same time, and they're not built to extend one another, but rather in parallel. And the reason that happens is because larger blocks take longer to propagate through the network, or if you create them really, really quickly, then you create one before the other was heard of by a different node. So the blockchain starts to look a little bit like a block tree. And what that means is basically, right, we have a lot more forks in this chain, and this implies several things. First of all, we are losing a lot of capacity. Everything off of the main chain is something that we transmitted but didn't take in some sense. All payments in there are not considered as part of the history of events, only things on the long chain. It turns out that the rewards that are collected by the nodes who do the hard work are skewed. They're not in proportion to the amount of effort that they invest anymore. So this is also something pretty bad. And maybe the most disturbing thing is the security of the protocol starts to degrade because somebody can show up again with a long chain and do a double spending attack like I've shown you before, basically displacing the work of the honest network. And it takes less work to do it than before because all of these blocks that the honest network built were not forming a very long chain like they should have. They're actually competing with one another instead of extending one another. So the security goes down, and this is a graph from such simulations. So I want to stress that this is actually a very politically charged topic. People are actually fighting over this in the Bitcoin world. There's a very difficult debate that caused Bitcoin to splinter into several currencies, and it's still ongoing. So the scalability problem that we started working on quite before that became very relevant. So the way that we started addressing this problem, other than the analysis of it, was through different protocols. Basically, we proposed several changes to what Bitcoin should do instead of picking the longest chain. One of our protocols is called Ghost. It just picks a different chain than the longest one, which turns out to be slightly less susceptible to double spending. And we've recently released another protocol called the Spectre Protocol, which does away with chains altogether. So our proposal is to replace Bitcoin's blockchain with a direct acyclic graph of blocks. So every block here, instead of pointing to a single predecessor, points to several ones. And this data structure lets us do more interesting things. And here I'd like to point out that most of our intuition comes again from voting. So as I explained, the Bitcoin protocol is something that you vote for the longest chain. Here, in the Spectre protocol, we do pairwise voting. And this intuition came again from social choice. What Spectre does is actually recursive voting. So every block runs a voting procedure on its predecessors and then copies their vote, in some way trying to amplify the votes of everyone that came before him, trying to reach consensus again. So I won't go into the details. You can read the paper or find it on my website if you want. And I'll just say that there are other very interesting solutions to scalability. Some are discussing off-chain transactions, things that go on outside of the blockchain itself, but are somehow tied to events on the blockchain. There are many other attempts at improved protocols by many others. This is just a selection. Maybe the last thing to touch on is the incentives in the protocol, right? So we can always wonder if the incentives are aligned. We know that they aren't. In fact, large miners can deviate from the protocol and gain more payments if they do so correctly. So there was actually an important result by Itai Eyal and Emin Gunserer from Cornell, who described a deviation from the protocol called selfish mining, in which the attacker withholds his blocks. He creates a block and doesn't tell the world about it. So sometimes this is a very bad thing because the network builds a longer chain than you, and your block is eventually void. But sometimes you manage to build maybe 2 of these secret blocks, and you can throw away the blocks of the honest network. And it turns out that when you analyze this strategy, you can somehow show that sometimes you profit. So what we were interested in is knowing and understanding exactly how to solve this problem, and maybe the way to begin was to understand how to do deviations even better. What is the optimal deviation that you could do? So it turns out that you can start to think about this as an MDP. So first, you can think of the length of the attacker's chain and the honest network's chain as a state in some MDP. You can think of actions, and you need to show that these are indeed sufficient, where you adopt the chain of the honest network, or you try to override it, or you just keep building it secretly. And what you get is eventually a policy that tells you what to do for every length of chain that you have, every length of chain of the attacker. And we have an algorithm. It's not exactly an MDP because the reward function is nonlinear. We had to do some clever tricks to get it to reduce to MDPs. But basically, that's the way we solved it. So this very technique gave us the optimal attack, which gives us bounds on how safe we are from it. And more importantly, maybe, it gives us a new security analysis for Bitcoin. We can use the very same technique that we did for selfish mining to go back to double spending, this original problem I talked to you about, and do a better job with that. So maybe the last thing, if we have a little bit more time, is to just mention this network level security that I talked to you about before. You can try and disrupt communications in the Bitcoin network on purpose. I've done so in 2 papers with colleagues from Boston University and from ETH. In one way, we attack the way that nodes form the peer-to-peer network. In another paper, we try to do attacks on the infrastructure layer of the communication to disrupt Bitcoin and see what we can get out of that. And maybe the more interesting part is to try to solve this problem. So in a paper with Sarah Tochner, my student who's here, that we presented in a workshop on Sunday, we tried to do a game theoretic analysis of how to pick your neighbors in this peer-to-peer network. Right? So every node that is on the network has a list of known peers. Some of these are attackers that have gotten their messages to you and are in your buffer. And from those, you need to select your neighbors. So the trick is to do this selection in a way that keeps you connected to the network and not disconnected. So that is also our attempt to improve Bitcoin and see what happens. So I'll stop here and conclude, I suppose. I hope I convinced you that cryptocurrencies are an exciting application area for computer science. There are contributions in this field from many, many areas, and that includes AI. I think AI is going to have a larger role to play in the future. There are many, many challenges and open questions. I just touched, I think, the tip of the iceberg in that respect. And I guess since we started in 2011, I'd really like to go back to 2011 and maybe this time buy more Bitcoins, right? It would be nice. So I'll stop here and thank you all. Right.
Thanks, Aviv, for the great talk. Given that we are running out of time and there are some meetings that take place in the lunch break, I think we'll have to stop here and postpone the questions to offline. I think Aviv will be around for, well, till the end of the conference, I hope. Yep. Right. So thanks, everyone. So that concludes the first early career session. Thanks.